So you can see an example of a graph here. This is a snapshot graph. One question that you might ask yourself is, well, what type of oscillation creates a sinusoidal wave? And the obvious answer is that it's a sinusoidal one, right? When you have a block moving up and down on a spring or anything else that has simple harmonic motion that gives you a sine curve, you're going to get sinusoidal waves. That means that a lot of what we already learned about oscillations is incredibly relevant to what we are going to do, in the sense that we've studied things like amplitude, period, frequency. All of those things are still going to be very relevant to us. So you can see here that we still have an amplitude for this wave given by the height of the sine curve. If you're making a snapshot graph, we have a slightly new concept, which is called wavelength. You can see it labeled on the picture here. Wavelength is measured, is symbolized by the Greek letter lambda, which you can see there. And the wavelength tells you how far in space you have to go to get from one crest of the wave to another crest of the wave. So that's the definition of the wavelength. And again, a question that we can ask here is, what happens to a little ant that is riding on this wave? And it's going to give us the other kind of graph, which again is called a history graph. Now we're zooming in on one point where the ant is located. And we're trying to capture how is the displacement changing with time. I mean, you'll notice that here we still get a sine wave. So again, sines and cosines are going to show up a lot throughout this part of the course. And again, the period, which we've seen from oscillation motion, shows up and is the amount of time that it takes to go from crest to crest, right? So period and wavelength are analogous, but they're somewhat different. And again, just like we explored frequency in the oscillations part of the course, frequency, which you can write as 1 over the period, is still very relevant. You can also write an angular frequency, which is 2 pi divided by the period. If you want to put these two motions together and think about, well, I want to know what's going on in space and I want to know what's going on in time, and I want to think about how those work with each other, what you end up getting is a thing called the wave speed, which is basically how fast is the wave traveling? How fast is it propagating from one place to another? I mean, you can actually calculate it by multiplying the frequency times the wavelength. One important thing to note is that this is not the speed at which individual molecules are moving, for example, right? If I think about in a sound wave, there is every little air molecule is moving at a different speed as the wave propagates. That is not the thing we're finding here. This is how fast is the whole disturbance moving from one place to another. All right, so to kind of conclude our initial discussion of waves here, I'm going to build this kind of parallel model with oscillations, right? So here's our oscillations model. You can see all of these fun quantities. We've got displacement, amplitude, period, velocity, right? We have this sort of sine function model for oscillation that depends on time. We're now going to basically add space to that model, and everything kind of steps up a little bit. So instead of just having omega t plus phi inside of your sine function, you now have a kx showing up in there. And that k is just the numerator version of the wavelength, so that we can put it in the numerator instead of putting it in the denominator. That k is typically called the wave number. And it kind of relates how wiggly the function is, the wave is in space.